Capacitors can store electric charge and release that charge when it is necessary. This is most basic definition of capacitors. We have already heard a lot, but this definition is ambiguous. What it means, what exactly a capacitor do in a circuit. I know there are a lot of videos about capacitors, but this video will be different. In this video, I will talk about capacitor application in circuits, not its inner structure or other trite stuff. In this video, I will answer these basic questions. Where in a circuit should I use a capacitor and how to select its capacitance? In this video, I'm gonna bring you 10 examples of capacitor application in circuits with practical experiments that show you what exactly a capacitor do in a circuit and what will happen if you ignore using capacitors in your project. Please stay with me in the rest of this video. As you already know, capacitors are available in different types, shapes, and specifications. The difference in capacitors' specifications is caused by the difference in their inner structure and the material used in them. I don't care where these differences come from, but the differences themselves are important. Main difference among capacitors are in their speed, frequency, ESR, ESL, price, polarity, capacity, shape, size, and stability to change in environmental conditions. These parameters force us to select and use one of them in a particular application. This is an electrolytic capacitor. It can store a lot of charge, but usually its working voltage and frequency is low. This type of capacitors are sensitive to environmental conditions, especially temperature. Let's do a simple experiment. I'm gonna measure capacitance of this capacitor using my LCR meter and see what happens when temperature go up and down. Nominal capacitance of this capacitor is 100 microfarad and its real capacitance is 87 microfarads. There is about 13 microfarads difference between its nominal and real capacitance. Maybe it is corrupted or something. So I'm gonna heat this capacitor up using my lighter and then cool it down using this freeze spray and observe what happens here on its real capacitance. You see, when I heat it up, capacitance go up, increase. And when I cool it down, its capacitance go down. We can conclude capacitance of the capacitor change in different environmental conditions. Electrolytic capacitors have polarity. I mean its leads are not same. I mean this lead is not same with this lead. On one of leads, there is a marked line like this. This dashed line indicates negative lead and other lead is positive lead. This fact forces us to use these capacitors exclusively in DC applications. Electrolytic capacitors are most known capacitors among non-specialists. First application of capacitors is to use this type of capacitors in rectifier circuit to reduce ripples. Application number 1, using electrolytic capacitors to reduce ripples in rectifier output. This is a simple rectifier circuit. This is main AC voltage source, this is 9-volt transformer, and this is a full wave rectifier. Let's set it up and see what is going on here on output. This waveform represents the DC voltage on rectifier output. Look here, these horrible ripples makes this voltage almost useless. To eliminate these ripples, I am going to use an electrolytic capacitor here on output. Be careful about capacitor's max voltage and its polarity. This is rectifier output after using an electrolytic capacitor on output. Don't be fooled by the deceptive appearance of this good-looking boy. It looks constant and steady. But if you draw a few milliamps, voltage will drop and those ripples will come back again. I'm gonna use this power resistor to draw a few milliamperes and see what will happen on output. When I put a resistor on output as load, those ripples appear again. You may ask why electrolytic capacitors are used in rectifier circuits. Because they are relatively cheap and they can operate in main voltage frequency and they are available in high capacitance. You may ask another question, how much should be capacitance of this capacitor? It depends on many parameters, but easiest way to find out is trial and error. You have to increase capacitance of this capacitor until ripples on output voltage become tolerable to your circuit. Application number 2, dealing with high instantaneous current. Sometimes there are components in circuit which have inrush current, and this can cause a lot of problems. This is a simple diagram to turn a DC motor on or off using a microcontroller. If you look closer to this diagram, by knowing DC motors have inrush current, you can conclude when the DC motor turns on, inrush current will cause serious voltage drop in VCC. What we can do, how we can deal with this problem? Best way to deal with this problem is to use a complicated and costly inrush current limiter circuit. Employing inrush current limiter circuit will help to extend life and efficiency of DC motors in addition to its prevent of voltage drop. Maybe it's a good method, but it doesn't worth it to use inrush current limiter circuit in all of your projects. Sometimes, in some cases, you can use a single capacitor to prevent intolerable voltage drop. You can use a capacitor in this way. In a start moment, a portion of inrush current will be covered by the charge stored in the capacitor. The larger the capacitance, the lower the voltage drop. Try to place the capacitor as close as possible to the motor. Dealing with inrush current is not the only challenge when you have a DC motor in your project. The biggest problem is to deal with noise emitted from DC motor. It's a real disaster. Application number 3, DC motor noise elimination. This is a simple 1.5 volt brushed DC motor. I am gonna run it directly with my power supply and probe its leads with my oscilloscope. As I expected, this unsettled situation in power line will bring down any microcontroller. In order to improve the situation a little, we have to use a capacitor in this way. I'm gonna use this 100 nanofarad capacitor in this experiment. Let's see what will happen. Magic. Most of noises are gone. And when I remove the capacitor, noises come back. Let's see it again. This is awesome. Now remaining noise is tolerable to many microcontrollers. You may ask why 100 nanofarad capacitor is used there, or how to reduce noise even more or remove it completely. To answer first question, I have to say that each capacitance of capacitors can bypass a special range of frequencies or noises. For this motor and many other motors, 100 nanofarad will work fine and will be good enough. But if you have another DC motor which 100 nanofarad capacitor doesn't work at it, you have to find the right capacitance for your DC motor. To answer second question, I have to say that yes, you can reduce noise even more by using multiple capacitors with multiple capacitances or by using advanced RLC filters, but I think it doesn't worth it. If your project is very sensitive to noise and can't tolerate that noise, it is better to replace your motor with a high-quality, low-noise motor instead of trying to reduce noise. This type of noise is not limited to DC motors. Wherever a mechanical component is used in electronical product, this type of noise will appear somewhere in the project. Let's consider this guy as example. These tactile switches are present in almost every project. Our next application is about these mechanical switches. Application number 4, debouncing push buttons. This is most simple push button circuit. I am gonna set up this circuit and probe the point A with my oscilloscope. Here you can see normal voltage on point A is 5 volt. But when I press the button, voltage on point A dropped to 0. And when I release the button, voltage on point A come back to 5 volts. Look here. This diagram seems to be clear and sharp, but if you zoom it, you will discover a horrible phenomenon. Look here at these noises. These are bounces. Let's look at another one. And here, and one another. This one is really awful. When two contacts of a button hit together, they tend to bounce off of each other a few times before settling down. Most of mechanical switches have this bounce problem. You have probably never noticed that bouncing because it only lasts for a very short period of time. For example, it lasts for 1% of a second. In the first sight, it seems harmless, but if you use point A on this diagram as input to microcontroller, it will be extremely annoying and it will disturb the microcontroller. To remove those bounces, to debounce these buttons, you can simply use a single and tiny capacitor parallel with the button. Now I'm gonna put a 220 nanofarad capacitor parallel with button and test it. All of those bounces disappear from signal and it is clear now. It seems our capacitor worked fine. You may ask why I use 220 nanofarad capacitor. There are formulas available on internet to calculate best capacitance to debounce a particular button. But in most cases, 220 nanofarad capacitor will work fine. You know, it is not only button bounce or DC motor noise. You can eliminate or at least you can reduce all kinds of noises using a simple capacitor with proper characteristics like proper capacitance, proper ESR, ESL. These types of capacitors are generally called bypass or decoupling capacitors. Let's talk more about it. Application number 5, using capacitors to eliminate general noises. I know you have heard about capacitors which block DC and conduct AC. There is a joke about this behavior of capacitors. They say capacitors block DC because DC voltage hit these plates like this and can't move on. But AC pass these plates like this. Let's consider this behavior of capacitors to understand what exactly it means. Most of real-world signals are composed of multiple simpler signals. Look at this simple signal. This signal is composed of a 2-volt DC and a sinusoidal with frequency F. If you put a capacitor with proper capacitance related to frequency F parallel with this signal, sinusoidal part of the signal will pass the capacitor and goes to ground, and DC part will ignore the capacitor and will reach the load or receiver. If there were multiple sinusoidal waves with different frequencies along with DC voltage, you can use multiple capacitors with different capacitances to pass those frequencies to ground and have fun with your beautiful and clean DC signal. This is the way who designers eliminate noises with different frequencies in their projects. To be honest, professional designers eliminate noises using RLC filters. An RLC filter consists of capacitors, inductors, and resistors, and they are more accurate than a single capacitor. I will explain those filters with examples and experiments in one of my next videos. Now it is better to continue our discussion about capacitors applications. I already said that if you put a capacitor parallel with a signal, it will pass AC part to ground and let DC part to reach the receiver. Now, what do you think will happen if you connect a capacitor in series with a signal? It will bring us next application of capacitors. Application number 6, coupling capacitors. Look here, if you use a capacitor in series with your signal in this way, it will block DC, but it will conduct AC. For example, if you apply the signal to left lead of this capacitor, it will block DC and deliver sinusoidal wave to its right lead. It is used mostly in amplifiers. Let's do a simple experiment. Here is a microphone pulled up with 2.2K resistor. It converts sound waves to voltage signal with a DC value. Let's set up this circuit and probe point A with my oscilloscope. Hello? Hello? Look here, these are my voice signals shown on oscilloscope. Look here. This signal is a combination of sound waves with a DC part. When I was talking, waveform of my voice was displayed on oscilloscope. The signal shown on oscilloscope was combination of sound signal itself and a DC value. Usually amplifiers work with sound signal itself and we have to remove DC part. How we can remove DC part and let sound signal itself to pass? Yes, exactly. The answer is wholly capacitor. We can simply put a capacitor here in this way and let the magic happen. I'm gonna use a 100 nanofarad capacitor here. This yellow signal shows voltage on point A and blue signal shows voltage on B. The DC part of yellow signal is removed and the signal itself dropped down to 0. Look here. Hello, hello, hello. This is the magic of capacitors. You may ask questions like, why I used 100 nanofarad capacitor? What is impact of capacitance to this circuit? What will happen if somebody used 10 microfarad capacitor instead of 100 nanofarad capacitor? To answer these questions, I have to explain more about capacitors' behavior. Capacitors block DC voltage and pass AC, but something is not mentioned in this phrase. Yes, capacitors block DC voltage, but when the capacitor is fully charged. When the capacitor is not filled, it passes both AC and DC. If a signal have a DC part, like this signal in the circuit, it will fill the capacitor to its DC value first. You may ask how much time it takes to this capacitor fully fill. This capacitor is going to fill by this resistor here. It depends on resistance of this resistor and capacitance of this capacitor. But you can see effect of this capacitor on oscilloscope. I'm going to put a 10 microfarad capacitor instead of that 100 nanofarad capacitor and see what happens. Look here, now capacitor is fully charged. I'm gonna discharge it with these tweezers and see what happens. This signal is going down. It means the DC part is eliminating. After a certain amount of time, it will reach to zero, and it means the capacitor is filled. Increasing capacitor capacitance will cause more delay in reaching signal to zero. This is one of reasons why in old analog devices, when you turn them on, they would start with loud noise for a moment and then they would go normal. Mostly because of the time coupling capacitors inside their circuits take to fully charge. The higher the capacitance of coupling capacitors, the slower the DC part of the signal get to zero. What it means in fact? Delay. Usually delay is unpleasant thing, but sometimes it becomes useful and bring us next application of capacitors. Application number 7. Employing capacitors to make delays. Sometimes we need delays to make electronical timers. There are so many solutions. Using capacitor-resistor combination is one of them. I'm using this op-amp here in comparator mode. It means if voltage on its positive input is greater than its negative input, then its output become active and it will turn this LED on and turn this transistor and then this motor on. But if voltage on its negative input is greater than its positive input, then its output is turned off, it is deactive, and it will turn this LED off and turn this transistor and then turn this motor off. Voltage on point A is set by middle lead of this potentiometer here. You can adjust this potentiometer to change voltage on point A. Let's assume that voltage on point A is 2.5 volts. Voltage on point B is equal to voltage of this capacitor here. If you press this button, this capacitor will charge to 5 volt immediately and voltage on point B will jump to 5 volt. And then because positive input of this op-amp is greater than its negative input, this op-amp will turn the motor on. But if you release this button, voltage on point B will gradually decrease from 5 volt to 0 volt. While voltage on point B is greater than 2.5 volt, I mean voltage on point A, the motor will stay turned on. But when voltage on point B go under 2.5 volts, the motor will turn off. It means if you press this button, the motor will start to run immediately, but when you release this button, the motor will stay turned on for a while, and after that the motor will turn off automatically. Let's set up this circuit and see how it works. It works fine. You can adjust amount of delay with this potentiometer. Let's adjust it. Look here, delay is decreased. I can increase the delay this way. This is delay for a long time. It's okay. We are not done with capacitors applications yet. Another capacitors application which I am intended to introduce is to use capacitor as sensor. Application number 8, using capacitors as sensors. You have seen one of them already in this video. Capacitive microphone. This is one of them. There are other sensors which are made of capacitors. Capacitive sensors like temperature sensors, pressure sensors, touch sensors, humidity sensors, and so on. Using capacitors as sensors is not our last item. There are some others. Application number 9, using capacitors in capacitive power supplies. I have already said that capacitors are conductive in AC. This characteristic of capacitors makes it possible to use them to build capacitive power supplies. Capacitive power supply, also called capacitive dropper, is a kind of power supply that uses capacitive reactance of capacitors to convert high AC voltage to low DC voltage. I will explain them in detail in one of my next videos. Till now, we considered capacitors applications and where to use them in our circuits. But sometimes we have to use capacitors somewhere in our circuit without knowing exact reason. You may wonder how it is possible. I'm gonna explain. Application number 10, items recommended in datasheet. Sometimes we need to use a special IC or module in our circuit, like NE555 timer, LM2596 switching regulator, microcontrollers, etc. If you look at datasheet of those ICs, you can find minimal setup diagram for those ICs. In most cases, there are capacitors in minimal setup diagram with predetermined values. Maybe you don't know what exactly they do, but you must follow those recommendations for your circuit to work properly. So, I have mentioned 10 applications of capacitors in circuits. I know there are a lot of other applications this useful component have, like snubber circuits, whatever. If you know other application for capacitors, please write it down in comment section for me. Thanks for watching. If you like this video, make sure to subscribe for more.